Hello everyone. So in here, I want to present about the shortest path on 2D grid map. I want to introduce myself. My name is Abian Amroajis with student ID 2415101057. Focus on comparing two popular shortest path algorithm, breadth-first search and Dijkstra algorithm in a two-dimensional grid environment. On the outline presentation is divided into 5 sections: background, algorithm design, followed by the experimental setup, result, and analysis. Finally, the key finding and future recommendation. Background, important topic in computer science because it's widely used in many real-world applications. For example, GPS and vehicle navigation, Google Maps, and then autonomous robot and drones, computer game AI and PCA movement. And the last, logistic and smart transportation. The problem formulation and objective. How can BFS and Dijkstra be implemented on two-dimensional grid? How do they compare in terms of execution time? How do they compare in path quality or length? Which algorithm is more efficient for unweighted graph? To answer this question, we implement both algorithms in Python and tested them on different grid size. Before discussing the algorithm, we need to understand how a grid can be represented as a graph. In graph theory, consists of vertices and edges. Consider a vertex while connection between neighboring cells are represented as edges. Movement is only in four directions: up, down, left, and right. Obstacle block movement cannot be traversed, is to find a path from the start node to the goal node. Breadth first serve is to explore node level by level, use a queue data structure following first in, first out principle. BFS guarantees the shortest path. An unweighted graph time complexity is O V plus E, where V is the number of the vertices and E is the number of edges. BFS is often the preferred solution for unweighted pathfinding problem. BFS always explores the nearest node, so the first time it reaches the goal, the path found is guaranteed to be the shortest. In Dijkstra is designed for weighted graph with non-negative edges cost. Instead of queue, it uses a priority queue min heap. At each step, the algorithm selects the node with the smallest tentative distance. This allows it to find the minimum cost path even when edge weights are different. However, maintain the priority queue introduces additional computation. As a result, time complexity becomes O V plus E log V. Dijkstra is more powerful because it can handle weighted graph, but that flexibility comes at the cost of additional computation. To evaluate both algorithms, we create grid environment of three different sizes: 10 by 10, 20 by 20, and 50 by 50. The start position was split at the top left corner, while the goal position was placed at the bottom right corner. Random obstacles occupied approximately 5 to 10% of the grid. The implementation was written in Python using the DQ library for BFS and HackQ for Dijkstra to perform metric, path length, and execution time. Experimental result show that both algorithms found path successful for all grid size. Both algorithms produce exactly the same path length. For example, on the 50 by 50 grid, both algorithms found a path length of 99 steps. However, BFS requires less execution time than Dijkstra. This indicates that BFS is more efficient for unvectored grid environment. execution time comparison. In this chart is to highlight the execution time difference more clearly. The difference is relatively small for smaller grid, but gap become larger as the grid size is increased. On the 50 by 50, BFS completes the search significantly faster than Dijkstra. So this trend is consistent with the theoretical complexity analysis of the two algorithms. Complexity analysis. The reason behind the performance difference lies in complexity of the algorithm. BFS has a time complexity of OV plus E, which essentially linear. In contrast, Dijkstra has a complexity OV plus E log V. It must be repeatedly maintain a priority queue. All edges costs in our grid are equal. The additional work performed by Dijkstra provide no advantages, but in BFS achieve the same path quality while requiring less computation. In unweighted graph, Dijkstra solve a more general problem that necessary making BFS the more efficient choice. Both BFS and Dijkstra successful found valid shortest path in all test cases. The path length produced by the two algorithms were identical because the grid is unweighted. BFS is more efficient on unweighted graph, fastest execution time on all grid size, with the gap widening as grid increase. Dijkstra excel on weighted graph. Its priority queue mechanism makes is the correct choice when edge costs vary. For the recommendation, weighted graph use cost-based grid to be better showcase Dijkstra. Advantage over BFS when edge costs vary. And then more algorithm include A, Bellman, Ford, Warsman, and Greedy best first search for broader analysis. And the larger grid size will be try to scale up to 100 by 100 and 200 by 200 to observe how complexity scales with the environment size. On the real application, test on actual data, OpenStreetMap, or robot simulation. So I think that's all that I can explain in this presentation. Thank you.